Good morning, all. Today there is a change in your timetable. This lecture will be conducted for image processing, and 2:30 lecture will be conducted for AI. Now, what we discussed last time was convolution. I told you few steps regarding to convolution. First step is if two functions you have, you will think it they are f tau, ft or tau, whatever the variable you want to keep, and the another variable is h tau. So you will have two variables, or rather two functions. You will have two functions. Okay, and then what you are doing is first step that you have to do with the convolution is flip, shift, multiply, integrate. There are four steps regarding to convolution. You know how to flip. So I will flip it by negating my variable. So I'm flipping it. So this is flipped version of my window. And shift is adding or subtracting some constant. If I'm adding a constant, negative constant, then also it is a shifting. So this is my uh, shifting. So this is my shifted by, this function is shifted by t. This function is shifted by t. Okay. So this is shifted. So this is flip. This is flip. This is shift. Multiplication of this two. This is multiplication of this two, and integrate over minus infinite to infinite, minus infinite to infinite, and you get it for d tau, where which is tau is a variable of your integration, it is dummy variable. And what you will obtain is convolution between what? Not f tau d tau, ft dt. What is t? T is the point till what you are shifting. This is the symbol of it. Field star. I am not going to feel it, but it is a field star, which is a symbol of convolution. Sometimes asterisk is also used instead of field star. So both of them are symbol of convolution. For better understanding of the same thing, there is a diagram given in this visual explanation is also given of the convolution. There are two functions ft and gt. In our case, it was ft and ht. I hope it is visible to you all. Two functions are there, ft and gt. So first of all, what you have to do, you have to flip this function. Ft I am keeping as it is. You have to flip it. To flip, what I have to do, I have to just take. So what I did just represented instead of t, I represented in tau. Instead of t, it is represented in tau. Okay, so this representation in ft dt, I did it in terms of f tau and d tau. That is what I did here. F tau and h tau, or f tau and g tau, whatever. Right? Then flip this. So you represent it in another variable, and then you flip the g of t. So this is g of minuses. You can see it is flipped version. You can see it is flipped version. Whatever was available at 1, it is now available at -1. Whatever was available at 4, it is now available at -4. And you can see it is looking like a mirror image of this. It is flipped version, right? It is mirror image. Flipping is what? Mirror image with respect to one axis. This is your axis. So this is how it is flipped. Okay, now what you have to do? You have to bring this. So what you have to do? You have to take this to minus infinite location. You have to take it to minus infinite location. Okay, so you will. What you will do? You will keep your. This is my f tau. I am going to keep. I am going to keep this g tau in the infinite location. I'm going to keep it on the infinite location somewhere here. Right. At infinite location, you can assume this is my g of t, and I will see what is. So I have shifted it to infinite location. So I am actually calculating f of infinite convolves with f of minus infinite convolves with h of minus infinite. That is what I am, or f of minus infinite convolves with g of minus infinite. What is the meaning of that? My t value is minus infinite. I am shifting by minus infinite. So it is somewhere here. Okay, then I'm saying what is the multiplication value? Multiplication is what? What is overlapping? That is what, when if there is overlapping, then only then there will be multiplication value. Because if there is no overlapping, what will happen? Wherever this function is non-zero, see my g function is non-zero at somewhere at infinite, but at that time my f of tau is 0. Wherever my f of tau is non-zero, at that time my g of tau is 0. So they are not overlapping, they are not having any common value at some location, and hence multiplication is going to be 0. So no meaning of convolving there. Where the convolution will start? Whenever it will somewhere it will, whenever multiplication will start when they will have something in common. So whenever the function will be like this, na, at that time by shifting from minus infinite somewhere here, it will come somewhere here, then it will come here. At that time, multiplication will be non-zero, overlapping will be non-zero, and some value will start. So when multiplication is non-zero, what to find out? When multiplication is non-zero, then find out minus infinite to plus infinite integration of that multiplication. That is what we are doing. This is multiplication in bracket and d tau. That is what we are doing. So actually what we are doing, that we are finding area under the multiplication. We are actually finding area under the multiplication. So here what will be the area under the multiplication? Very less, because a line is just in common. So there will be something in common, right? Then I will keep shifting it somewhere here. So here this is my function. So now what will be multiplication? Multiplication will be overlapping is this much. So multiplication is going to be higher than the previous case, and hence area under the multiplication, as I highlighted, that will be higher, and hence it is going to get increased. And then I will keep shifting. I will keep shifting up to infinite. Okay, so that is what then I will repeat the task again. If you want to understand it thoroughly and better way, we can go with this. There are two functions, what we can say, two rectangles. There are two rectangles. I am not sure whether the white animation is not working. We can see last time we have seen that animation, right? We need to. I think it is in editing mode. That's why. I guess it is not working. Let us see. Okay, so here, so if you can see, there is one function. There is a rectangle. There is one function. There is another function which is also rectangle. So actually, what I want to do is I want to multiply I want to do convolution of two rectangles. Let us do that here. I want to do convolution of two rectangles. Okay. So I have one rectangle. This is my h of f of t, and another is my h of t. Okay, so first function is, both are rectangles of same size. Okay, now our first task is what, this is at 0. It is at 0. This is also at 0. Both are having the same size. What is my first task? This is my h of t. Then I am representing it as h of tau, and this is f of t, or you can represent it as f of tau as well, because we are just changing the variable name. Can anyone tell me what will be h of minus tau? What will be h of minus tau? Anyone is getting idea here? If two rectangles are there, if I want to flip rectangle which is symmetric with respect to vertical axis, yes, it will be same as h of tau. Yes, so flipping of h of tau is going to be same as h of tau. Yes, true. So what we are having is, I am just making it. I can write it as h of minus tau as well, because it is flipped version and the original version will remain same. Okay, then what is my next job? Just take this one and keep it to infinite. First, you keep it to infinite. What is area under the multiplication? Because wherever this is non-zero, this is zero. This is my function. Blue is my another function, right? Whenever this is non-zero, at that time this is zero, and when this function is non-zero, at that time this function is zero. So area under the multiplication is going to be zero for all the time till my function will come somewhere here, right? Now area under the multiplication will be this line, because it is a multiplication will be non-zero for this line, and area under the multiplication is this much only. Then what I will do, I will keep shifting it. So I've shifted it somewhere here, I shifted it somewhere here, and you can see area under the multiplication will increase. Then again I will keep shifting it somewhere here, I will reach here. I hope you can understand. I am shifting my h of tau all the time. I'm shifting it. I will make it like this, I will make it like this, and it will be non-zero. I will do it till my multiplication, area under the multiplication will be non-zero, right? So can you think what will be the shape of my area, or what will be the shape of the area? We can repeat the task. We can repeat the task with some another way also. See, okay. Now what I will do? So you know what I'm going to do is I will start with this point where area under the multiplication is non-zero. Till time no meaning of doing that, right? Because area under the multiplication or multiplication itself is zero. So here my multiplication is going to be non-zero. So area is very less. So I know area is very less. Then what will happen? I will shift it further. I am going to shift it further. I am going to shift it further. Right? I will shift it somewhere here. Okay. So now what is the area under the multiplication? You can see this is the area under the multiplication. Okay. So it increased. Then further I am shifting it somewhere here. I will keep shifting my function. No? So I am shifting it here. I hope you can understand. What will happen to area under the multiplication? Area under the multiplication increased. It increased. Right? Then what will happen? It will further increase. It will increase. It will keep increasing till both of them are overlapping with each other. Right? They will overlap with each other. Totally overlapped. Then it is a maximum area. Then what will happen? Suppose I keep shifting, what will happen? Suppose I keep shifting, it will decrease. So can you think what will be the shape of this convolution? How is the convolution look? Yes, it will look like triangle. True, it will look like a triangle. Okay, so that is what is shown here with the animation. I think that you can see that as well. Here, the blue one is your actual function. Red one is the flipped version of your rectangle, which is same. Then it is kept to infinite. It is scanned through your function, and the triangle that shows the black line shows the convolution values. That again you can see. What is going on? See, two functions. The blue one is original. That red one is flipped version of the another function that you can see here, and the black line is the convolution as expected. If you want to see one more example, here also you can see this is my original version. This is flipped version, and you can see the area under the convolution. You can understand. You can see the convolution. You can see the convolution, right? So this is what the concept of convolution is. The same thing already we did. We did a discrete function f of x. We had w of x. We flipped it. We scanned through the entire f, and we multiplied and summed it up because it was a discrete function. I hope you can understand the concept of convolution now. I am repeating it again and again because it is highly important concept for the entire subject. So I think you should be clear with the concept with the animation. I think it's very much clear now what the operation is. In short, you have to remember just four operations. What are they? Flip, shift, multiply, integrate. That's it. And I know that if filtering, if I'm doing the filtering, filtering is also the same process. We were doing, see what we are doing in the filtering, if you remember 2D window we are taking, we are flipping it, but flipping of that symmetric window, we have taken all the time symmetric windows. So flipping of symmetric window will remain the same as the original window, as was the case here, that flipping of the function of symmetric function was same as the original function. So we were flipping the window, but it was symmetric, so we were ignoring that step. Then we were keeping on the first overlapping point. Then we were having element-wise multiplication and addition. Element-wise multiplication and addition is nothing but multiplication and integration. For the discrete function, we have to do the summation only. Then we shifted to the next pixel. Then again we kept the neighborhood and the window. Then we multiplied and summed it up. So filtering, you know, is the heart of image processing. And filtering process is nothing but the convolution process. And this is the broader view of the convolution process for continuous signals. What we had was the same process but was for the discrete one. I hope you are able to relate the two cases. You are able to relate two cases. Right? Now we are going to so now I know that anyway I'm going to do convolution with my image because I'm going to do filtering. I may smooth my image, I may sharp my image, I can do any operation with my image. So if I am doing convolution with my image in spatial domain, then what is the impact of that convolution in my frequency domain that I want to learn? If I am having so that is what my next job is, that what is the impact of convolution in frequency domain. So now suppose h of t is my window and h of mu is frequency domain of that filter. H of t is my filter or window or kernel, whatever you want to say. H of mu is frequency domain representation of that H of t or filter. It is frequency domain representation of my H of my filter, frequency domain representation of my filter. This was, this is what, this is my f of t is my image, and this is frequency domain representation or Fourier transform of my image. This is Fourier transform of my image, and this is frequency domain representation of your filter. Okay, so now what this convolution theorem says, what my convolution theorem says, if my function is convolved in time, if my function is convolved in time, if my function is convolved in time or in spatial domain, then a Fourier transform of that convolution, that is Fourier transform of a filtered image, will be equivalent to Fourier transform of my image will be equivalent to Fourier transform of a filter image will be equivalent to multiplication of individual Fourier transforms. So what is so now we have two methods to filter. See, observe here. We have two methods to filter. One is what, I will have my h of t. I will have my h of t, and I will convolve it in my I will convolve it in my in my spatial domain with my image, as I used to do that. I will keep it on first pixel, then shift to second, third, and I will have element wise multiplication and addition. If I can do that, and I can obtain my filtered image, that is one way. That is one way. Or another way is what, I have image. So what I will do, I will find out Fourier transform of my image. So I obtain this, right? Then I will have my filter in my frequency domain. How to have the filter? Like you can say it is Fourier transform of this kind of thing. Fourier transform of this I have. So what I will have, I have actually this and this. So what I will do, first of all, I will find Fourier transform of f of t. I will find Fourier transform of h of t. I will multiply them, both the Fourier transform I will multiply. And then if I take inverse Fourier transform on both sides, if I take inverse Fourier transform of this, what I'm going to obtain is, if I take inverse Fourier transform of this, I'm going to get my filtered image again. Two ways to find out filtered image. One is convolved in the regular spatial domain, so you can obtain this. Another way to obtain this is what? Find out inverse Fourier. If I find inverse Fourier transform of this, what will happen? Fourier inverse Fourier transform of Fourier transform will be this function itself. Inverse Fourier transform of, if I am finding inverse Fourier transform of this multiplication, then also I am going to get my convolved image. So what I can do is, I have my image, I have my filter. I am going to find out Fourier transform of both. I will multiply them, and I will find out their inverse Fourier transform. Okay, so two methods you should be. Of course, we will take them in detail, and they will come. They will come in detail. We are going to take. But if you remember, we took that this process we have already gone through. We did this process. I told you that we will do it. I will explain you the why it can happen later in fifth chapter. We did it. I can show you that also. Wait, just a minute. I can show you that also. Already we have gone through this process. See here, if you remember, this. What was this? This is Fourier transform of my image. This was my Fourier transform. This was Fourier transform of my image. This is f of mu, which I wanted to filter, which is having this type of noise. That's why I want to filter. So this is what I did. I have my image. So I want to filter it out. I want to clean it up. So what I will do, I will find out this is Fourier transform f of mu, and this is h of mu. This is my h of mu. This is Fourier transform of my filter. How to obtain this is remaining. We will do that. Then what we did? What we did? How we obtained this? So I told you that how we obtained. If you remember what we did here, we multiplied this two. We multiplied this two. And what happened? Because we multiply here, these values are 1, these values are 0. So this multiplication in this region was multiplied with 0, and this region was multiplied with 1. So this region remained as it is. This region suppressed. How? Why it suppressed? Because we multiplied with this, right? So this was multiplication. So what actually we did? We did f of mu into h of mu. That is what we did. And then how we obtain, if I will do multiplication, it is going to look like this only. Just these dots will not be there. Then how to obtain this image back? So we did inverse Fourier transform of this. That is what we did. Now already we have used this. We have seen this. It was this function only. It was this function only. So I hope you can understand what we did earlier. Again, we will take it more in more detail, but basic idea you must be clear with. So this is another way to filter. This is another way to filter. Okay. Now, before we use this, before we understand, before we take more details over this, we should prove this. We should be clear with this. We should prove this. So what convolution theorem says that if you convolve in spatial domain, multiplication in frequency domain. So Fourier transform of this convolution will look like multiplication of individual Fourier transform in frequency domain. Another duality property, spatial domain convolution, frequency domain multiplication, spatial domain multiplication, frequency domain convolution. So these two are known as convolution theorem. This is known as convolution theorem. This is duality property, convolution in spatial domain, multiplication in frequency, multiplication in spatial domain, convolution in frequency. We have to prove this. So proof is how to take the proof. So first of all, what I have to do, I just have to start with this point. I will start with this point. I want to find out Fourier transform of this f of t convolves with h of t. I want to see whether it becomes this or not. Whether it becomes this or not. So now, for that, so what we can do is we can have it like, okay, what is Fourier transform of minus infinite to infinite? Before we take this Fourier, okay, what I have? So let us have this f of tau. This is convolution f of t convolves with h of t. The convolutions Fourier transform will look like e raised to minus j 2 pi mu t. Okay, this is the definition. This is e raised to pi j pi mu t dt. This is how we will start. What I will do, I will substitute the value of f of tau convolves with h of tau. What is f of tau t convolves with h of t? F of t convolves with h of t is given by this integration. It is given by this integration. So substitute that value here. So how it will look like? It will look like this. Okay, it will look like this. It is looking like this, right? Now, I will change the order of integration. That is very easy step that we generally used to do. That is possible to change that order of integration. So I am doing that tau I will take outside, t I will take inside. So tau, this term will not vary with respect to t. That's why it will come out. This terms varies with t, and hence it will be inside the integral. This theta will come out. This is the term which varies with respect to t, and it will come inside. And this is dt. Okay, now what is this? Observe. What is this? So this is Fourier transform of h of t minus tau. So now let us take, so you can see this is the definition of a Fourier transform of h of t minus tau. Now what I am doing is I am taking t minus tau, I am taking t minus tau as x. I hope you will understand this tau is equal to x. So now what will be value of t? T is x plus tau. Substitute those values here. So what is dt? What is dt? Here in case of this integral, tau is a constant. In case of this integral, tau is a constant. So, so what will happen? Integral will be just dx. Integral will be dx because tau is a constant for this integral. Okay. So dt is equal to dx. substitute those value here. So what I am going to get, I am just writing about this in small this bracket, square bracket. So this will be h of t minus tau, that is x. What will be this exponential? Exponential will be e raised to minus j, then 2 pi, then mu. What about t? T is x plus tau, and this is dx. What will be the next step further? What will be the simplification of this? If you will take this, you can separate out this exponential. How it will look like? It will be like e raised to minus j 2 pi mu x into e raised to minus j 2 pi mu tau. E raised to minus j 2 pi mu tau is constant with respect to x, so I can take it outside. What I can take it outside? E raised to minus j 2 pi mu tau I can take outside. What will remain inside? What will remain inside? So what we can say, this will just vanish, this will just vanish, and this is what will remain. Now can you tell me what is this? Observe what is this? Which definition it is? H is not impulse, Mayank. Is H impulse? See the definition. Yes, it is H of mu. Actually, it is for a definition of Fourier transform of my H of x. Function e raised to minus j 2 pi mu x. Right? So this is for definition of Fourier transform of my H of H of x, or we can say it is H of mu. X is a variable of your integration, right? So it can be t, tau, whatever you want to keep, right? So this is actually definition of your H of mu. What is the h of mu? It is h of t e raised to minus j 2 pi mu t dt. Or instead of t, you can use x as a variable of integration, right? So this is actually h of mu. So what actually you obtain? This is nothing but h of mu into e raised to minus j 2 pi mu tau. That is Fourier transform of h t minus tau. Fourier transform of h t minus tau is nothing but h of mu into e raised to minus j 2 pi mu tau. Okay, that we will substitute here. So whatever we will get as our term, substitute it here again. So what we will get here is integral. We will get it as integral. Then f tau. This is f tau. Then h mu. This will be h mu. Then exponential e raised to minus j 2 pi mu tau. I am not writing all, but it is a j 2 pi mu tau and d tau. I hope you will understand. This is a e raised to minus j 2 pi mu tau d tau, and this is f of tau. This is f of tau. Now, if you will see, this h of mu is constant with respect to tau, so it will come out with the integral. It will come out of the integral, and what will remain inside? F of tau e raised to minus j 2 pi mu tau d tau. What is that? F of tau e raised to minus j 2 pi mu tau d tau. If you want to see it further, it will look like this. I substituted that value here. H of mu is constant with respect to that. So inside only this terms remains. What is that? It is f of mu. See, tau I cannot take because tau is a variable here. Tau is time domain representation. This variable will come as your output. Jamie, I can show you the definition if not clear. I can show you the definition. Are you clear with it? See here, what is the definition? Whatever variable we are using here, na, that will not come out. The variable which is available here, which is this frequency domain representation, that will come out. Na? Okay. So this variable should be changed to this variable. That is what the meaning is, right? So that is what we obtained here. So now it is f of mu, and this is h of mu. This actually you can say take it as t or tau, whatever you want to keep, but it is actually f of tau, whatever you want to keep. Variable is your choice now. So that is what we obtain. So what is our conclusion finally? Our conclusion is that Fourier transform of the convolution results into multiplication in multiplication in frequency domain. So if I take my filter, if I take my image, I convolve them, and if I find Fourier transform, I will keep it on one side. I will take my two individual Fourier transforms and I will multiply them. I will keep it on other side. Both results will be equivalent. That is the meaning. Okay. Now, what about this proof? How will you prove this? So easier, I guess. Of course, you can start like Fourier transform of this multiplication and all those things. But easier method will be what? Find out inverse Fourier transform of this. Then substitute a definition of convolution. Then do the same process as we did. Inverse Fourier transform is nothing but it is also having the same definition, just exponential instead of negative, it is positive exponential. That's it, right? So what is expected that you will start with the inverse Fourier transform. That inverse Fourier transform of this is this. If I can prove that, then it is also proved that the Fourier transform of this is this, because they are. It is possible to go on both the domains without any loss. So I will find out inverse Fourier transform of this. So what I will have, I will just find out inverse Fourier transform. So definition of inverse Fourier transform will come here. Then definition of convolution will come here, and the same process will be repeated. And that is your assignment you are going to do by yourself. Okay. I'm not. That is very easy because same steps are there. Just exponential value will be positive. Otherwise, same logic, same methodology will be followed. And you are not going to, you can take inverse Fourier transform of a function is you can find out inverse Fourier transform of n function, then you can definitely say Fourier transform of this. If you can find out this is the inverse Fourier transform, then you can definitely say this has Fourier transform which is this. Okay, so fine, that we are going to that is your assignment that you are going to do. So what is our conclusion regarding to convolution theorem? Uh, Multiplication in time, convolution in frequency, convolution in time, multiplication in frequency. That's it. Now we will repeating again because I repeated again because it is, as I told you, it is highly useful. These words will be useful when we will do some operations. So keep these words in your mind. Now we are moving towards slowly towards the image, because image is not a single one-dimensional function. My image, you can see my image as 2D function. It is 2D signal actually. What is the value? What is signal? It is having varying value. If I want to draw a signal, what will happen? Like it has value 3 now, then it has value 5 now, then it has value 100 now, then it has value say 75 now. So if I draw like this, then can I say it is my discrete signal, right? But in my image, what happens? I have pixel value here. Suppose its value is 3, then value is 5, then value is 100, then value is 75. So in one direction already it is a signal, but my image doesn't complete there. I have varying values in other direction as well. So you can think like my image is two-dimensional signal, two-dimensional varying signal, two-dimensional discrete signal. So you can think like image is 2D signal. Signal is what it should vary with respect to one axis. It should have different value. It is varying with respect to some axis, right? And we our image is having two direction values, and they are varying in two direction. So now whatever concept we have studied for one direction, now we have to extend to two direction. That is 2D. Two-dimensional in two-dimensional I have to extend all the concepts, and then I will implement them on the image. So we are moving gradually towards image. So now I will start again with the impulse. What was impulse? Impulse was sudden occurrence. But now, uh, but now here what is the case? Here my impulse will have now it is in two dimensions. So when my both the variables, my both the arguments are zero, my impulse will suddenly occur. Otherwise, it will remain zero. So now if you can see, this is my two dimension, one is t axis, one is z axis, and this is my, of course, third axis is needed for the amplitude. So this is t, and this is z. Okay. When both of them are zero, I hope you can see the dimension here. All right. So if both the values are zero, then my impulse has infinite value. My both the variables are zero, then my impulse has infinite value. Okay, so this is what my two-dimensional impulse is. When both the variables are, when both the arguments are zero, it has infinite value. So now, what is the area under the curve? So area under the curve will be 1 as it is because it is impulse. But my t and z both will vary from minus infinite to plus infinite. My t and z will vary from minus infinite to plus infinite. So so this is area under the curve. In both axes, I have to take integral from minus infinite to plus infinite. That's it, and it will be 1. That we have already know. That we have seen this. What is next? What is next? It is shifting property. It is shifting property. What was shifting property? If any function is multiplied with impulse and integrated from minus infinite to plus infinite over both the axes, then what will happen? Then what will be the result? Result is function where impulse exists. Where this impulse exists at argument is equal to 0. If I equate this is 0, it exists at t is equal to 0. If I equate this at 0, that is it exists at z is equal to 0. That means this impulse exists at t and z is equal to 0, 0. And that's why this integral will remain. Integral will result into function where impulse exists. That is function at t is equal to 0 and z is equal to 0. That is f of 0, 0. This is what shifting property is. Now someone say, okay, no, but we don't want to get at 0, 0. I want to get at t 0, z 0. Then I have to take my impulse at located at t 0, z 0. You can see my impulse is located at t 0, z 0. So my impulse is shifted by t 0 and z 0 somewhere here. Suppose this is t 0, this is z 0, and t 0, z 0 value coordinate will come here, and my impulse is located here. This is location of my impulse, T0, Z0. This is Z0 and this is T0. So if my impulse is located somewhere here, then my impulse is located somewhere here, then what will be the shifting property? Shifting property will be like function multiplied with impulse integrated over infinite axis results into function where impulse exists. This impulse exists at T0, Z0. It is right shift by T0 and Z0. It is right shift. So what I have assumed here, this is my positive axis, this is my negative axis. This is my positive axis and this is my negative axis. That is what my assumption is. That's why this is T0 and Z0 if I am taking delta T minus T0. If I want to shift on this side by T0, I should take delta T plus T0. Or if this side if I want to shift, I have to take T plus T0. Okay, so what will be the result function where impulse exists? It exists at T0, Z0, and that is what my result is. So this is shifting property. For one dimension already we have gone through. This is for the two dimension. This is just extension. Now, next is my discrete impulse. Discrete impulse, if you remember, we just changed it infinite to 1. Instead of all the axes, we took that discrete values, right? You can see the discrete values are taken. So if both the arguments are equated to 0, my impulse is 1, otherwise 0. And you know that shifting property will look like not integration, but the summation of function multiplied with impulse summed over minus infinite to plus infinite. Result is where function where impulse exists. This impulse existed argument is equal to 0, which is x0 and y0. Same logic you can apply here. That this you can see that this impulse is shown here. This x0 y0 impulse already I think you can understand. This is x0, this is y0. Impulse exists at that point and value is 1 there. Okay, so this is shifting property for two-dimensional discrete function. The function where impulse exists at x0, y0. Now, Fourier transform for the two dimension. What is Fourier transform for the two dimension? Earlier, what I had f of t e raised to minus j 2 pi mu t dt. Now I have another variable z as well, so it will be f t z e raised to minus j 2 pi mu t plus vz. It is vz. Earlier, the variable, whatever the task was done by new variable, that one frequency axis. What I actually had is, I had t, and I obtained f of mu, which was having the values like this, capital F of mu. So I had frequency domain representation of axis t was mu. right? But now I have two dimensions, so I will need two-dimensional frequency domains as well. And the frequency domain representation of this, if I say this is my z-axis, so frequency domain representation of this z-axis will be v. So now in mu t, same way vz, and so definitely this for dt I need to extend with vz. And what I will get, I will not get just f of mu, but I will get f of mu plus mu v. I will get mu v. And now not only mu is my frequency axis, but v also is my frequency axis. Mu corresponds to t in time domain, v corresponds to z in time domain. What is inverse Fourier transform definition? Just exponential value is positive now. What we had f of mu e raised to z 2 pi mu t d mu. Now we have f of mu v because I will have frequency domain with me. So I will have f of mu v with me. Then I will have exponential here and it will be the definition d mu dv. Integration with mu and v. Okay. Now the same, so I think this is clear, definition is clear to you. Now the same example that we took for that one dimensional, I mean ft, the same example we will take. What was that example? Of rectangle. We spent sufficient time on this rectangle example. That example I am talking about, this one. So here what I obtained, here you can see what I wanted to tell you is that it is having t and one axis only and its amplitude. So what I obtained was mu xt, I obtained mu, and for f of t I obtain f of mu, right? But now what I have, this is extended in two dimensions. This is not having only, it is not varying in t axis, it is not varying in the t line, it is also varying with respect to z line. It is also varying with respect to z line. So I will not just obtain f of t, I will also obtain f of v. That is actually I will obtain f of mu v. Now I wanted to extend the same example into dimension. How it will actually look like. This is the dimension. If you can see properly, see, this is my axis. You can see the t-axis. This is z-axis. Okay. I hope that that is t by 2. It was minus capital T by 2 to capital T by 2. Remember, that is how was. So that is already true here. From I can see. So here it is also varying from minus T by 2. See the width. You can see this width is. You can see. I hope you can see that rectangle. So see this position. If not, it will do you. I think then if we will observe on this t axis, it is from t by 2. It is starting from t by 2. It is starting from t by 2. It is starting from t by 2 and goes up to t width. It is starting from t by 2. It is starting from t by 2 and goes up to t width. That is, it will go up to minus t by 2 on other side. So this is varying. So if so, this is minus t by 2 to plus t by 2 having t value, and sorry, minus t by 2 to plus t by 2 having a value. From the z by 2 to it is also z. So from, if I start from z by 2, if I go up to z, so it will go like the minus by 2. So then only total width will be z, na? Then only total this is z by 2, this will be z by 2, then total width will be z. So this function is very by 2 to minus t by 2 is also a. Instead, like only we're having value from minus t by 2 to plus t by 2 having value a. So now it is the same example. It is the same example. I hope you can relate it with this. right? So now we have to find out, see the same thing, right? Here, instead of the width was w by 2 to minus w by 2. Now to separate out t and z, we have taken capital T. Right? So that is all right. I hope you can understand it. Now, now we have to find out Fourier transform of this. So everyone should start thinking on this, how to find Fourier transform. It is now what I will do. I know it is two-dimensional one, so I will use this equation instead of any other equation. I will just use directly this equation. This equation I am going to use. Now tell me what is my next step. Integration and this type of example you have gone through so many times. So quickly tell me so that we can reach to some conclusion immediately. Should I integrate from minus infinite to plus infinite now?
picture, they are getting giant set of data, right? And what might they use it for? You never know, right? I mean, of course, there will be the idea is mostly going to be win-win situations, right? But then they are storing without knowing the purpose of usage. I mean, one purpose for now is from the end user, right? Let's say you store your code into Git, so your purpose is solved to just have a repository. But why Git? See, I'm not claiming anything. I'm just making a scenario. Why? How Git will be benefited, or the community will be benefited again by the Git, anyways. But then you may not know all the purposes ahead of time. You even may not know a single purpose of uses of storing that data in advance, but you'll just say like, okay, let the data come in, okay, and that's the data may be structured, semi or unstructured. You just store maybe in a data lake or distributed file system like HDF or some NoSQL databases, right? So just let the data come in. I mean, we don't care for their schemas for now. Let the data come in. What will we do with this data whenever we might have some purpose at hand? That is, you may say like, now it's time to read that data for a purpose. At that time, actually, you will realize some required schema on a partial part of the data. See, we may not do schema for complete data set. No, the data is still there. However, it is stored in the internal data structures of MongoDB or HDFS or maybe data lake, right? The data is still there. However, it is stored in the data model or in the data structures, internal data structures, right? But now we will use some other applications for that required purpose, for the purpose at hand. You may have multiple purposes. Know that you may have multiple purposes, right? And today you have one purpose. A few weeks later, you may have another purpose, and likewise, like fourth. Data is still there as is, right? But then we will now create schema as we need based on the purpose. And that's exactly the query first approach can also mean, right? I mean, you think of the query and then, you actually build the metadata or the schema. But then see that there are multiple levels here. The original data is still there in any of the, such tools, right? Or you can in general say data is still there in data lake. Data lake, right? Now it's time to use it for a purpose. Then when you will have a choice to utilize certain tools, for example, MapReduce or Hive, like QL, etc. Right? So for example, what we are going to learn today in a while is Hive query language. So what will happen? You will still have data maybe in any of the underlying sources. Right. I will also talk about change of sources. Do remind me from Hadoop to Spark or TEZ Tage. Right. Do remind me of that. But know that when you have a purpose now, you will choose a tool, for example, Hive, and then you will start creating schema, and you will fire your query, and you will get your analytics or insight. Right. That's what called schema on read. So there are few more layers or levels here. The underlying data is still there, which is mixed. Then on top of that, you are going to run an application, but that application itself will create a schema now. So there are two layers, we may say, of data itself, right? So the one is underlying data where internal data structure is being utilized, but the another is the schema for a purpose, right? That's what it is called, schema on read, right? And it's very much like query first approach. Okay, so fine. So please be aware of such things. I should also add this term, whatever Ria mentioned, in a side note. Query first approach, right? So that we don't miss such stuff, right? Um, Also, okay, fine. So I believe you all are at least having very good practice of bookmarking and I mean bookkeeping your work, right? So please, I would advise you with being, proficient, uh, professional, right, efficient and all, uh, do utilize some or other medium to, bookkeeping your learning and your work, your own understanding. Okay, do utilize some or other medium for that. Okay, so with that, we'll move on to next topics for the day, right? Any questions so far? So we know schema on read versus schema on write, right? It's a concept only, ideology, we can say, right? Uh, Fine. Anybody has any question? Nothing much, right? Okay. All right. So we'll move on. What is it? Oh, okay. Still 20 minutes. Okay. Okay. I will also share this high level aims. Let me just grab that. Wherever is it? Okay. I will also talk about high level aims quickly. Then we'll go to high QL. Come on. Yeah. Here. So yesterday I reminded you about this particular tab. I am not certain if I'll give you another version, like maybe high level aims version 2. Okay. This PDF file. Uh, so we talked about fraud detection, right, as one of the application, then how to detect live traffic. We talked about few of these. I think we talked about them, right? Uh, yeah, this is one more which we can talk about. How do you identify the communities in a given network? Now, this can be network of people, okay? I mean, the people around the globe, okay? For example, for the what should I say? For election campaign, right? The person, I mean the group of or the candidate for the post, right? He wants to propose or focus on different communities so that he can actually, for example, let's just say USA and President Trump, for example, he wants to also focus Indian community, right, or technical community, right, uh, which are there. So given the network of people, and you got to find out, communities, and then you for a betterment of everybody, you may find a purpose, and then you will focus them for a campaign, right? So such things are also done with the use of big data and analytics, right? That like there are people who are connecting as a community to both, then this can be termed as spreading from group to other group, right? So we have to find out a person who is actually involved in both the groups. Then we'll just give him the message. Then we expect that he will spread it in group one as well as group two, because he is the connecting point, right? So such things are also part of high level aims of big data and analytics. This list will keep growing. I might have missed few yet, but I'm working on my bookkeeping part. I'm trying to dump whenever is immediately possible, right? So dead ends, in the community, or roles, right? Dead ends you may want to find. This is one more thing. I don't remember the name of the application which we used to, refer back in maybe 2008 or so, where I was interested in buying a house in states, uh, in certain community, right? But I was also looking at the prices and the amenities, right? So this can be again, done or achieved by the big data analytics part, right? Rare events, I talked about it yesterday, right? Effective web search is, anyway, you all are doing machine learning for, the feedback by people, and, right, we are already working on that. Okay, this is one simple thing, just to convey another topic also. What my customer are talking about my products and services. Read this question again. What my customers are talking about my products and services. If you want to answer this to the CEO, right? He asked this question and you want to answer. Of course, you will have to bring data and proofs, right? Traditionally, the architect would go and look into the RDBMS systems or data warehouse, etc., right, to get information. But then nowadays, from where he will look it? Any idea? Let's say you are a company and you want to actually find out what your customers are talking about your products and services. Will you just refer to your own data sources, like which are primarily dealing with the website or the app, mobile app itself, or you will also go and look some other places? Right. Devang says public forums. Yeah. So that's the thing. The picture has changed now. Right. To answer this, you don't just need to look at your own data sets. You have to actually bring in more data from, for example, public forums or review or feedback. So, Jaimin, review or feedback is definitely one thing, but that review or feedback can be, of course, it was in the intermediate times, review and feedback. These were always there on many websites as one of the contact us or feedback kind of Google, not Google, just a form, right, on a certain website, right, or maybe star, just to give a star when you just go for a product or service, so that the company will know how it is. So that's one thing, right? On your own system, you have a mechanism to get the review. That's one thing. But then nowadays, the market has to go beyond, right? Beyond the paper forms, beyond the forms, digital forms themselves, right? The market has to go beyond, because customer will be talking to each other as humans. They may be utilizing so many apps to communicate to their friends, colleagues, etc. That's when that has given one more platform to find out the reviews. So review from public forums, like somebody's talking about his or her purchase on a private chat, or maybe on Facebook, or likewise like forth, right? So such all things would be counted towards the feedback. So they all, and as we know, such things are huge. The data is mixed, like schema and semi, and that's when the big data analytics come into picture, right? So fine, we understand what point I had to make. So there is a change, right? Traditionally, there was just paper form, then let's say digital form on a website for a feedback. But then nowadays, it's beyond that. That's what we understand. Moreover, a few more, high-level aims with respect to banking, right? Let's say bank wants to give loan to somebody, like house loan, right, or give a credit card to somebody. He will, I'm sorry, the bank will have to uh, find out, right, whether the person is good or not. I mean, credit-wise, right? So how, or you may think how companies might be calculating credit scores, right? So all these things can also be, based on the big data analytics, possibly, right? And this is all theoretically what you're learning in your machine learning, like dimensionality reduction, etc. That can also be supported by big data analytics. So high-level aims, this will keep growing. Okay, you also kind of bookkeep for yourself the high-level aims, so that this is very much like, for example, Reliance Industries, how they will venture into new businesses, right? They will connect, their own data. I mean, they will learn from market, and then they'll venture into new businesses based on the learning from them, right? Fine. So we'll now move on to HiveQL, okay? Because Monday we'll have lab. We'll continue talking in the lab also about Hive. Are you able to see my screen? I'm sharing a PDF file which reads curl operations and more using Hive query language. One of you please respond. Are you able to see my screen? PDF file? Okay. I'll just drink a It reminded me about carrying a water bottle to every classes wherever, physical room number 3 or room number 2 or 1 4, whatever, right? But then in online, we keep talking continuously. It is always a good practice to take a break, right? At least for water. Okay, so let's talk about Hive. Fine. So good time, right, to start on Hive. And you already understood schema on read concept, right? So imagine you are just let the data flow and let it be stored in your HDFS or MongoDB. You don't really care for their purpose. I mean, you don't have a purpose as of now. Or fine, see, my daughter is attending her class, and mom is angry, right? Of course, because the daughter will not sit. So how about you guys? I mean, okay, you are all 18 plus, so but your parents will be still, after you many times, right? And you will have excuse, ભણું છું મોબાઈલમાં, but we don't know, or you know what you might be doing with mobile, right? Know that you have, convenience. Don't just misuse stuff. Of course, balance. Okay, utilize mobile for entertainment, fun also. But then, you also have a future to make your career, right? Okay. Moving on. HiveQL, right? So in Hadoop ecosystem, yeah, it's part of Hadoop ecosystem. But then it was actually the newer versions are common also. Why it was part of Hadoop ecosystem, we'll learn about it. Okay. So out of many, one more mature component is Hive. It is mainly used for performing SQL, and the data will of course be residing distributed, right? Now, for the workforce, when I say workforce, it's nothing but employees, right? Uh, for the workforce, having skill set SQL and not programming, right? Hive is a handy tool to perform data analytics with Hadoop framework. So those who are not, into MapReduce Java program or likewise, but they are good at SQL, that's when they may, choose Hive to get their, purpose and their result. The query language supported by Hive is also sometimes referred to be HiveQL, maybe HQL. Okay. Know that here H is not HBase. Okay, here is Hive itself. Anyways, and we also know Hive. I'm sorry, HBase was also one of the tool to refer to distributed files, right? So how HBase differs from Hive, I'll leave that as one assignment for all of you to work on. How HBase differs from Hive. Okay, that's one assignment for you. I'll also try to make an article, I mean, at least one topic or a material on Google Class and share, right? But you also should try to find out what is the difference. At least theoretically, HBase is known to be, online database. It's very much like your RDBMS only, but it's just that the underlying data is distributed, and hence it is a distributed database. Now, how can we term it as a distributed database? Then the answer is yes in a way, because it is letting you create schema, and it let you fire queries, right? So now again, when you say SQL, I should actually use this here query only, because SQL means structured query language, and I mean SQL will be fine here, because in Hive you actually create structure, and then on top of that you fire query. So that is very much like schema on read, okay, what I was talking about when I started. So for the workforce who have skill set of SQL, HiveQL is a choice, okay. Now, what you need to do, of course, you need to have Hadoop framework installed, right? Because at least Hive 1.x, it used to write relations in Hadoop distributed file system. Okay, now I should again be careful about this word. Uh, yeah, but this relations means actual tables, okay, the data, not the metadata, the data part. So this relation you can think of like tables, okay, with ER model, right? Start the Hadoop framework first because Hive writes the relations in Hadoop distributed file system, which is also called a warehouse. So there will be a physical location. Okay, I should not say physical. There should be a logical location in my goodness, in Hadoop distributed file system. For example, forward slash USER forward slash Hadoop and forward slash Hive, HIVE, for example. And this is a logical location in HDFS. And we know behind the scene, it might be scattered across multiple nodes, etc. Right? So that location will also be termed as Hive warehouse because those relations, the actual tables, their information going to be there physically in the HDFS, and that particular location will be termed as Hive warehouse. So when I say Hive warehouse, it's nothing but a HDFS location. Fine. So of course you'll have to create that HDFS location, right? So the steps for installing Hive: download and extract the Hive tarball to certain location. Maybe this is your native file system, right? Or local file system. So I would say forward slash opt Hive. Then create a warehouse, Hive warehouse. So for example, I created this forward slash user forward slash Hive forward slash warehouse. Now maybe at the time I would have, when I would have, practiced, I might have a separate user for, performing Hive queries. And that's when the user Hive might be the location for HDFS. And then warehouse is the actual, it's not necessary that this warehouse fall under the user who is going to use it. Maybe not necessarily. But for now, temporarily, we don't want to, have complexity of user privileges and all, you please just create this warehouse folder in the corresponding user of Hadoop itself, whichever you have created already, or your system user itself, okay, administrator of your computer, right? So forward slash user forward slash name of your computer user, which is also configured to be, run as Hadoop, right? And then maybe just say warehouse. Okay, this can be different also the name, but let's choose to be warehouse. So we created HDFS location named warehouse, which will be actually the Hive warehouse for us, right? And see this, there is also one more folder required, for example, forward slash TMP, and it is in the Hadoop file system itself. Uh, I'll have to cross-check that part. But then it is important that the privileges are available to the group, whoever is going to deal with Hive QL. Okay. So this was one of the requirement, and we know CS mode is changing the mode of or the authorization part, right? Um, so make sure the group has access to these locations. Fine. Then you might have to add environment variables, right? So wherever you have installed the Hive, and then add that as the Hive home simply, so that you can run from multiple places. Hive is internally bundled. This is important now. I hope you are still with me. You are seeing my screen, right? Uh, so Hive is internally bundled. I mean, when I say bundle, it itself means internally. So it is bundled with DB jar file, okay, in the lib folder. Now, have you heard about DB? Anybody? Fine, WDB. I mean, just find it out. Okay, what is WDB? Okay, and how does it differ from other what you already know? Okay, anybody has any experience with WDB? Now, see, you don't need to be expert when you but you at least have to have some idea, if at all you might have. Anyways, you already have SQLite, right? SQLite database. What other? Yes, SQLite, right? So what other? So if you know SQLite, when you want to deal with SQLite on your computer, it's a file-based database. I think, if I'm not wrong, am I correct? Those who have worked with SQLite and applications, is SQLite a file-based database? I mean, file-based database. So Nemis says yes. So what I have understood, and I have used it, SQLite, in the past, and I know, I mean, it just creates a file It was whatever requirement of mine when I did that, but it's been a while. Okay, so yeah, so basically, I mean, you can also think of, having that file move from mobile to desktop and back and forth. See if you can all achieve those things. But that is primarily with mobile applications and, stuff, right? But it is a file-based database. Suman also agrees. So at least we have 2+ for SQLite being a file-based database. That way, I believe DerbyDB is also a file-based database, okay? Uh, Okay, I'm using the word file based. I'm not saying fire based. Okay, there is some other term also. You all have used that part, right? Fire based, right? I'm not saying fire based. I'm saying file based. Anyways, so for now, know that DB is a database and it is RDBMS model. Okay, and there is of course a jar file, right? Java archive. So Hive, if you may go to lib folder, you may see a jar which actually has a DB, jar components, right? So what Hive uses DB for by default, it stores the metadata. And we already know when you create a table has a metadata and the actual data, right? So metadata will be stored in RDBMS, while the actual data will be stored in the Hadoop if you have, configured that way. We'll talk about other engines also, but for now, this particular PDF, like HiveQL Quick Start, is with Hive 1.x and it was then used with Hadoop itself. Okay. So, okay, let me repeat. Hive by default, Hive 1.x by default was coming with DerbyDB for storing, metadata. First thing first, you can also configure not to use DerbyDB and use MySQL or any other RDBMS system. For that, you'll have to refer this particular file named hive-site.xml. Fine. So explore that if you are interested. That's one thing. That's one level for metadata part, okay, which is less a schema on read part. The other layer, which is the bottommost, that is nothing but storing of the actual data, right, relations. So by default, it is HDFS, but then we'll also see other things possibly. Fine. So to be able to run Hive from any locations, of course, you will run from your terminal. Use whether you use what is it to be able to run Hive from any locations on terminal and still use the same metadata. Let us prefix the metadata location by configuration as below. Okay, I mean that's just one of the configuration. Okay, I would have learned that time. So yeah, this is very much like a connection string with JDBC, right? So connection URL, right? Have the configuration this way in this so and so file, which is what JDBC Derby database name. Okay, so now this is your native file system. Okay, when I say OPT, this is native file system, right? And you say create equal to true. So you have to specify a location where the file-based database will store its database. So this metastore.db is the file name or of directory name. What is it? I think I forgot, right? Hopefully it is a file name. Fine. Okay. Okay, so there's one thing you got to do, right, for the connection string. Now, of course, you will need Hadoop Home, Java Home, right? You start your Hadoop framework also. But one more command you need to learn about is called schema tool. This is with respect to DerbyDB. You have to initialize it, on the DerbyDB. So this was the concern many times, your Hive, you might not be able to run it properly. Maybe you have forgotten to initialize your schema with DerbyDB. So you might have to run this command definitely very first time uh, and see if it is corrupted. You might have to run it again to get started. Okay. So schema tool dash db type derby and init schema. So run about it. Hmm? This is more about instantiating derby db. Fine. So run Hive from command line interface, right? You start DFS, start yarn, start history manager, verify they are up and running, right? And you then say Hive, right? HIVE, Hive command, and then you say show tables. If it's all okay, right? In the background, you may also see some process named run jar. Maybe that is the Hive application, right? Uh, So here, whenever I would have done that in the past, right, and we all understand all these things, right? So this was the new component when I started Hive. So I assume that this run jar is actually the Hive Yeah, students, there is an electricity failure here, right? And I'm connected to you by phone right now. My screen might not be visible immediately. Let me connect hotspot to the computer and we'll join you again. Give me a moment there, okay? Any questions so far on Hive? I mean, to get started. Anybody installed Hive already? I'm looking at the chat window. Did anyone install Hive already? Razi, I'm working, Dipu. Oh, where is it? Here. Are you able to listen me? One of you, please respond. Okay, fine. And the screen might be on hold for now. Let me just turn on. Oops. So the question again. Anybody installed Hive? Please respond in the chat window. What am I doing? So now means that's your iPod, Nancy, and you have iPad in your hand. Okay, wait there. Okay. Okay. All right. So yeah, I see some responses. Nami says yes, and Ria. So two of you, I believe, have installed Hive. Can one of you, at least Namis, can you tell me how, which platform and which version or anything, what you may know? Namis, which platform, Windows or Linux? Ria, which platform, Windows or Linux or any third like online way of doing it? So Ria has installed. Okay, no issue. Ria has installed on Linux. Fine. Okay. Uh, right. So Ria, you were able to successfully query also Hive. Okay. Others, please don't fall back. Keep trying. Your best to get with tools and learn about it. So this semester will be more like hands-on onto multiple tools. Then you will have a choice to move on based on the purposes you might have. Yes, I got electricity power. I'll just get it. Okay, fine. Just a minute, students. All right. So uh, fine. I'm switching to the device present screen. So you may have to change the tab. Okay, you may pin the tab another one. Uh, uh, Look at please another tab. I'm presenting from another device. The same material basically the Hive QL quick start. Okay, is getting loaded right now. And can you see my mobile screen now? Right, all of you, anybody? All right. So we just talked about right how to install Hive. Ria might be able to help more also if you might be facing issues. I mean, I will definitely help anyways, right? So you have temp folder and you have the warehouse folder, right? You got to make sure the group has access to those folders, the Hadoop folder specifically, and then come on. We were talking about bundled Derby DB, right? You can change that also. And what? How do you change? There is a way. Okay, you have to provide this connection string. Instead of that connection string, if you may provide MySQL, then also it will be possible, right? You start Hadoop, start initiate the Derby DB, right? Then run the show tables command, and if you're able to see, if it just says okay, that means it is you're good to move on, right? And This is how you create database, right? I mean, simple, create database and database name, right? Then you definitely have to say use try one, whatever the database name is. Now, this is again, you need to know how internally generates MapReduce jobs for queries, right? So when you say create tables, so and so thing, right? It will create the table, and for that it doesn't need MapReduce. Okay, for creating metadata, which it's gonna store into your Derby DB, right? Then what will you do? Look here. For example, you have some file named kv1.txt in certain example folder on your native file system in Linux. So you will like to run this command, load data local. That local says that this file is, local file system. So load data local in path and the path name, and then you say override into table, whatever the table you have created, right? And then you say select star from POX. So this is how it's coming up. Uh, Browse directory. So next thing, when you will go and check the warehouse of Hive under HDFS, remember we created this HDFS location for Hive warehouse. So what you will see, whenever you create a table, you will also see some entry, like forward entry with the table name, like the schema name. And when you will move files, actually from your local file system, Hadoop, that load data in file, what it has done from your local file system, it moved that kv1.txt to the Hadoop Hive warehouse. Okay. Then, if you might want to do analytics on that, this is, I think, one more example. You can create some table called invites, right? Put file from local file. To HDFS. Now, one more thing, I'll talk further. Okay. Imagine instead of local file system, there is already one file or more into your HDFS, some X location, and you want to move that to Hadoop Hive warehouse. Uh, I mean, you want to load into Hadoop Hive warehouse. Then when you load, this is one thing you need to know and remember. Hive moves the files. Okay, I repeat, Hive moves the actual files from location 1 to the warehouse. So if at all you want the original file to be, at the proper location in going forward also, you'll have to create a copy. It's very much like take a backup or create two folders. However, or the best way is have the files directly stored into the Hive warehouse themselves, because Hive warehouse location is HDFS location, right? Uh, Instead of storing files into some other X location of HDFS and then asking Hive to move or utilize it, it's definitely gonna move that files into the Hive warehouse location. That's one of the peculiarity about Hive 1.x. It actually needs all its required files into the Hive warehouse. Then only it can query and further. Okay. So best approach might be have your files themselves in the Hive warehouse. Okay. Or if it is outside and you need a backup, you need the copy at the original location, then you will have to backup and restore kind of stuff. Okay. uh, Fine. So Hive load data in path, right? It is being loaded. uh, what is next? I think few things are repeated. We'll have to find out why they are repeated. Yeah, this is the point what I made, right? Loading data from HDFS to Hive warehouse. That's again internal to HDFS itself. It will result in moving the file or directory within HDFS. You might want to copy if original file or directory also need to be retained at original place. I think you understand what I just talked, right? Fine. So at least this particular behavior, what I just mentioned, you can also practice it and confirm what it means. Okay. Uh, Try to load a file into HDFS at X location and try to run the Hive command to load the data. You will see that that file will be moved to Hive warehouse at the original location. When you will try to see whether the file is there or not, you will see that, oh, my file is not here. Why? At X location. The reason being Hive moves it. Okay, so there's just you have to be aware of that peculiarity. Anyways, you can run queries like this: select a dot bar count star from invites a, where a dot foo greater than 0, group by a dot bar, etc. I mean, very simple SQL aggregation queries can be executed on Hive, provided you have the data files into Hive warehouse. Okay, right away. Uh, Now, this warning came up at the time, and I had to move on at the time, so I couldn't, kind of move ahead with one more step. But can you please read this warning? What Hive 1.x has to say? All of you, please read this warning. What Hive 1.x has to say? Hive on MR means like Hive on MapReduce, right? And MR, when we say original with Apache HDFS. Okay, Hive on MR is deprecated in Hive 2 and may not be available in the future versions. Consider using execution engine. So, so one thing is your data, right? Where do you store, in HDFS or some other place? And another is the execution engine. Remember when I said queries internally gets converted into MR and MapReduce program, right? The MapReduce framework, the yarn of Apache Hadoop 2.0 will be executing it and giving you the results, right? So what this warning says that consider your execution engine. Execution engine mean to say the MapReduce which will be executed, okay, or just this query behind the scene, whatever logic it will be doing. You can also use other engine which are Spark and TZ. Okay, so Spark you're gonna learn. I'll also explore, and we'll see what can we do with that. Right, ma'am will also demonstrate. But you understand what this Hive query, when I ran and when I saw this warning, what does it mean? Current lab work is not considering this warning. It is just utilizing HDFS and Hadoop MapReduce itself. Okay, as execution engine. And I would have to find out which version I had at the time of Hive, but it was definitely not 2 point plus. It was not 2 plus. It was up to 2 only. Anyways, so we have seen this part, right? It starts the MapReduce program in the background, etc., and it will give you the results, right? Now for the lab, what time is it? I mean, I don't know. What time is it? How much time? Oops. Fine. So the next thing will be what we'll describe in lab also is going to be the Python program. Okay. You can always write Python program, and you can use it for querying and data ingesting, right? Which we'll talk about it in the next lab Monday. So see if you can install a Hive prior to Monday. Okay. All right. All right. Yeah. Over to you next presenter.
Good afternoon, everyone. Can you hear me? Hello, can you hear me? Okay, and can you see the screen? Okay, good. So we are talking about approximate inferencing in Bayesian networks, and we will discuss the random sampling and rejection sampling, two methods. We'll discuss a couple of more methods, and then we'll finish this Bayesian network part. So the idea was behind the random sampling was, since the Bayesian network is a generative model, we can generate samples. And our way of generating sample was to choose a random number, and based on the random number and the probability of a outcome of a particular random variable, we will decide the value of that random variable. And we believe that as the probability increases, the probability of choosing that value for the random number also increases. So based on that, we talked about this random sampling, where we discussed about creating a stick and dividing the region of the stick as per the probability of the random variable, and then project the random number which you have generated on the stick and see in which region it falls. So it is a kind of randomization also, but the randomization which is consistent with the actual probability distribution. So this is the samples that we generate by this are consistent with the distribution. So that's why we can use it for our inferencing. And once we generate such samples, like last time we generated these samples, once we generate this kind of samples, we can use them for inference. And our idea for inference after this, the inferencing would be easy compared to exact inference where you need to do exponential computation. Here, if you want to compute probability of E given not of M, then look at all the samples where M is false and count the numbers. After this, the inferencing will only be counting. So numerator is where you observe both E is equal to true and M is equal to false. The total number of samples where E is equal to true and M is equal to false. And denominator is total number of samples where M is equal to false. So count those numbers and you get the answer. So in this example, it was 1 by 2. So there are two samples where M is equal to false. And out of those two samples, one of them has E is equal to true. So the probability of E given not M was 1 by 2. So this is how sampling would simplify the inferencing process. And we can do everything in polynomial time. But we have also seen the limitation of random sampling. Like if the evidence variable, the variable on which the query is conditioned, if the evidence variable is not present in the samples, then we may get divided by 0. Or if the query variable is not present, then we might get 0 divided by 1. So we need to sample sufficiently so that all the evidence variables and query variables are there in the samples. Our values are consistent with the query. Only then we can get the proper answer. And for that, we talked about another approach of sampling, which is called rejection sampling. Rejection sampling is more or less same as the random sampling, but only difference here is we would reject all the samples where the value of evidence variable are not matching with the query. So to perform rejection sampling, we first look at the query. In this case, the query that we are looking at is this question: probability of J given M is false and E is false. So while sampling, we will see what value of M and E we are getting. And if we get M or E true, we will reject that sample. And we keep on sampling the way we are doing in random sampling. Right. So similarly, we did this. We generated these two samples last time, and then we said that the second one has M is equal to true, and that's why we rejected that sample. And we keep on sampling again, and we select all the samples where M is false and E is false, and based on that we perform our inference. So let me list out few more samples. We want samples where M is false and E is false. So let us keep this fixed. And B and A can take any values randomly. So let us say we have generated these 4 samples using the process we discussed last time, and we just revised this time. And we want to answer this probability of J given not M and not E. How would we count this now? give you the formula. The formula would be number of times j is equal to true divided by total samples, right? Because the evidence variable value is same as the query variable in all samples. So all sample contains j is equal to false and e is equal to false. Sorry, all sample contains value of, for all sample value of m and e are consistent with the query. Right, so this formula where number of samples where j is equal to true given total sample is same as saying that number of samples where j is equal to true, m is equal to false and e is equal to false divided by number of samples where m is equal to false and e is equal to false. Right. Because every sample has m is equal to false and e is equal to false. So total number of sample is same as m is equal to false and e is equal to false. So this will be, answer to this would be, in how many examples we have j is equal to true? 1 and total samples are 4. So answer is 1 by 4. Right? This is rejection sampling. So it might be possible that we have sampled around 10, we have done random sampling on 10 or 10 iterations of random sampling. But out of this 10, 6 were rejected because the value of m and e were true. M or e was true. And we are left only 4 where value of m and e are false, which is consistent with our query. And out on this 4 only we perform the inference. That is the rejection sampling in a nutshell. And we had seen that in rejection sampling, we need to reject so many samples. So that is a kind of overhead. So it is kind of random sampling. So running time would not be much different from random sampling. But if we can reject some variable early, like the first variable that we sample is in the evidence of the query and is not consistent with the evidence value, then we can straight away reject the sample. So there we can make it more efficient. But if the evidence variable is last in the hierarchy of the Bayesian network graph, and at last node if we have to reject the sample, then there is no benefit of using rejection sampling. So if the variable which is rejected comes deep down the hierarchy of the sampling, then actually this is same as random sampling, just that we are rejecting or ignoring few samples where the evidence variable are not matching. That we have to anyway do with random sampling also. Right, so this was rejection sampling. Any question on this, random sampling and rejection sampling? Okay, then let's move to the next algorithm, which is called likelihood weighing algorithm. This is a slight improvement over rejection sampling. What we were doing in rejection sampling was we were first sampling and then we were rejecting. So we first sample a random variable and then we see whether the value of random variable is consistent with the evidence value in the query or not. If not, then we reject. That was rejection sampling. So likelihood weighing says that why would we do that? Why don't we just fix the value of evidence variable so that you don't need to sample it at all? So the idea behind likelihood sampling is do not sample the evidence variable. Just keep that value fixed as what we see in the query. So the generating and rejecting phase is removed. And then add some probabilistic weight to that query and see that how likely it is to generate this sample. And remaining of the variables you can sample as the random sampling strategy. So let us see how it works, and then we'll go back to this statement again. So again, the same example. Same Bayesian network with burglary, earthquake, John calls, Mary call, and alarm. And we want to sample, let's ask the same question. What was the question we asked last time? J given not M and not E. So let us ask the same question. What is probability of J given that Mary has not called and there was no earthquake? And we want to perform likelihood sampling here, or likelihood weighing strategy. So what we do is, again, we list out the variables B, E, J. So order of sampling is from top to bottom, and left right you can choose arbitrarily. So B and E can come in any order. First you can sample E and then you sample B. But before sampling J and M, you have to sample A, because J and M are conditioned over A. And then again J and M can change the order also. So remember this, while sampling, you are sampling from root node to the leaf node, and neighbor node can change order, but otherwise the order is fixed. And what we say in first sentence we say that do not sample the evidence variable, fix the value given in the query. So which are the evidence variable in this example? Evidence variables are M and E, and both are fixed to false. So let us make them false. So we don't need to sample M and E. Let us make them false. So this is what we have done from this first line. Do not sample the evidence variable, fix the value given in the query. Now let us look at this third line first. Let us call it second line. Sample other variables using random sampling, what we were doing earlier. So similarly, we will sample other variables. Let me give some random numbers again. So let's say random numbers are x1, x2, x3. We want to sample 3. So 3 random variables will help us in finding 3 samples. So let's say this thing is 1000, 2000, and 3000. So can someone quickly give me value of B, A, and J from that? Or shall I repeat this again to make sure you got it? So let's again draw a stick of B ranging from 0 to 10,000. And only first 100 are up to true. And rest of these are false. At 100 is 0.001. That is our probability. Or it is 10. I guess it is 10, right? Let's make it 10. So that is 0.001. Probability of burglary is equal to true is 0.001. So let's say on the stick, from if the value between 0 to 10 are true, and rest of the values are for burglary is equal to false. So for this region, burglary is true, and for this region, burglary is false. And again, project 1000. So 1000 would go somewhere here. So that is false. So the variable we have sampled is Similarly for A and J, can someone tell me value of A and J depending upon the x2 is equal to 2000 and x3 is equal to 3000? So now while we are sampling for A, which part of the CPT we are looking at? We are looking at part where B is equal to F and D is equal to F. So we are looking at this part of the CPT to sample for A, right? Okay, some of you have already calculated. Maliha says A is equal to false. Emin also says that, and J is also false. Good. So the answer eventually would be A is equal to false and J is equal to false. And let us finish this A thing, and then you can do it for J. So for A, we are looking at the sample where B is equal to false and G is equal to false, and accordingly we will break the stick. So the probability of A to be true is 0.001. So again, 1 out of the 1000. So again, if you are breaking it from 0 to 10,000, value up to 10 would be, this is A is equal to true region, and this is A is equal to false region. And if you project this number 2000 on this line, it will be somewhere here. So A turns out to be false. And similarly, J will also be false, right? So more or less it is similar to random sampling, but the only difference is that evidence variables are now fixed. And and can we just fix the evidence variable, or do we need to think deeper? So the question here that we ask is how frequently or how often we get M is equal to false and E is equal to false in random sampling. Can anyone answer this? In other words, if I take if I take 10,000 samples at random, how many of them if I take 10,000 samples at random, how many of them will have E is equal to false? This is relatively easy answer, right? That is probability of not E. Exactly. So that is out of 10,000. So out of 1,000, let's make it simple. Out of 1,000, 998 sample would be E is equal to false. That is probability of not E. And probability of E was 2 by 1,000. Right? So we weight this sample. So we say that we have rejected so many samples, or we have ignored so many samples where E could have been false. So this weight of choosing E is equal to false is probability of 0.998. And similarly, weight of choosing M is equal to false. What is that weight? If you again sample 1,000, examples, in how many of them will have? Now the question is, M is equal to false. Probability of not M, yes, but not M where A is equal to, now it is conditioned over A, so it depends on A, right? So in this case, A was false. So I should ask question like M is equal to false and A is equal to false. How many times you would see M is equal to false and A is equal to false? So that is somewhere here where A is equal to false and M is equal to 0.01. Out of 100 samples, or out of every 100 samples, there will be one sample where M is equal to true, given that A is false. So for 99 sample, it will be false. So for M is equal to false, it is 0.99. So let's multiply them. Let us say this is and let's call this weight W. So weight indicates likelihood of this sample, and that's why this method is named as likelihood weighing scheme. So how likely that you will draw this sample if you are doing it completely at random? So that likelihood is defined by the probability of the fixed variables. So we have fixed E and M to be false. So look at the probability of E to be false and look at the probability of M to be false given A, and multiply by that weight. So that will be the weight of the sample. So this often you will see the sample. So multiply by 0.99 into 0.99 and whatever count you get. So out of every 1,000 samples, this many samples would be all false. Does this make sense? Okay, then let me sample one more variable, or let me add one more sample, and let's see if you can calculate weight here or not. So let us say this is F true. What will be weight of this sample? Can anyone calculate weight? E is fixed to be false, so probability of not E is fixed, right? Probability of not E is always 0.998, irrespective of what other variables you are looking at. Only change we will notice is with probability of not M given A. Maliha says 0.3 exactly. So probability of not M given A is 0.3. Yes, exactly. So this is 0.3. From where did we get this? We get this from here. Probability of M is equal to true given probability of M is equal to true given A is equal to true is 0.7. So probability of M is equal to false given A is equal to true is 0.3. Right. So the weight of drawing M is equal to false can take two different values. It can be either 0.998 or it can be either 0.999 or it can be 0.3. Right? So in this example, it takes 0.3. So let us again write this weight. That is 0.998 into 0.3. Similarly, let's draw a few more samples. Then this is, let's say, this is true, this is true, this is false. What will be weight of this sample? Again, same as the previous one, because A is true and M is false. So this will be 0.998 into 0.3. And let's draw one more sample. That is true. Let's make this false. False. So what will be the probability of this sample? Now since A is equal to false, you need to look at this part. It will be again 0.998 into 0.99. Right, so this is how we generate sample in case of likelihood sampling. The randomization process is same. The only difference here is the evidence variables are fixed. So we do not sample evidence variables, they are kept fixed. And we generate the remaining variables. And while we generate a sample, we attach the weight with the sample, which is actually the probability of the fixed evidence variables. So multiply all the probabilities of fixed evidence variables and call it weight of the sample. And this weight means that this often we want to see this sample in our completely random sample method. And now if you want to perform inference on this, how would we do this? So the inference now is, so again the probability of J given not M comma not E is number of times you see J not M and not E divided by number of times we see not M and not E. So now this count will be the count of weight. So this count will be count of weights. Or other sum of weight. This will be sum of weights. So if we compare it with the random sampling, in random sampling, every sample was derived with a confidence of 1 or with a probability of 1. While in this case, the samples are derived with different weight given the probability of the random variable. So that's why rather than counting everything as 1, we will count with given weight values. So can anyone quickly answer this? What is the count? In how many examples you see J is equal to true and M and E is equal to false? So example where J is equal to true where this. So this is one example, this second example. So there are two examples where J was true and M and E were false in all other examples. So sum of all everything. So this will turn out to be 0.998 into 3 plus 0.998 into 0.99 divided by sum of everything. So that is 0.998 into 3 we observe 2 times, so into 2 plus 0.998 into 0.99 again we observe twice, so it is twice. Right? Can anyone answer me? What will be answer of this? Can anyone give me the value? is simple computation, but just to make sure that you got the point. What will be the value of this? 0.5, okay. 0.5, are you sure? Okay, yeah, okay. Yep. Yeah, because you can remove the 0.98 into 0.3, and what you are left with is 1 by 2. So that will be 0.5. Let's try one more example. Probability of, let's say, B given. Since we have sampled for not M and not E, let us keep that only in the sampled variable. What is probability of B is equal to true given not M and not E? So how many samples has B is equal to true? There are two samples, right? These two samples have B is equal to true. So I think again it will, and one sample has weight of 0.998 into 0.3, second has weight of 0.998 into 0.99. So again it will turn out to be 1 by 2, I guess. Right, so this is likelihood weighting strategy. And if you have noticed, we have sampled for every query. So we look at the query and based on that we sample. This is how it is different from the random sampling, because we want to fix the evidence variable. So look at the query and sample, and when you have sufficient sample, you can perform the inference. Is this clear? Any questions on this? If there are no other questions, let's move to the last part. And best is kept for the last. So we will end the discussion on Bayesian network with this. And this is probably the one algorithm that you would remember at the end of all discussions. This is a very famous algorithm. Actually, one of the top 10 algorithms of 20th century. People also call it as one of the top 10 algorithms of machine learning. And this algorithm is named as Gibbs sampling. So this is also a sampling algorithm. The setup is more general. The Gibbs sampling is a more general framework which can be applied to any kind of probabilistic graphical model. But we will discuss now in context of Bayesian network. And then in future, when we are discussing some other topics, at that time we'll again bring this in and we'll discuss more general framework of Gibbs sampling also. But first, let us see how it works in case of Bayesian network. So again, the strategy is similar to likelihood weighing in the sense that we fix the evidence variable. So first thing we do is we fix evidence variable. So again, let's do that with the same example. We have variables B, E, B, E, J, and M. And we want to fix the variable. So for that, we need to know the query also. So let's use the same query. The query was J given not M and not E. Okay. Let's see, we want to answer for probability of J given not M and not E. So what we do is we first fix the evidence variable. So let us again fix them, and let's again try it for 4 samples. So let us make this false 4 times. and now we will sample B, A, and J. So up to this, the story is same as the previous case. Fixed evidence variable and randomly initialize other variables or sample other variables. But now there is some difference. Let me first figure out or tell you what the difference is. So in previous cases, the samples were not dependent on each other. I mean, the way we sample the second example has nothing to do with the first example, right? Because we have generated some random numbers and there are no dependency. So second sample has nothing to do with first sample. Similarly, third sample has nothing to do with second and first sample. Here the strategy is changed. Now we are using some knowledge of graphical model and we are trying to relate the sample. We are trying to make the samples dependent. So let's see how we do it. We are saying that first randomly initialize other variables. So let us say we have randomly initialized these three variables. Let's say we have initialized all of them to be false. We are initializing B, A, and F to be false. So B, A, and J to be false. So this is point number 2. So fixed evidence variable, this is point number 1. We have fixed evidence variable. Point number 2 is randomly initialized other variables. So we have randomly initialized other variables B, A, and J to be false. Now something interesting. Sample one variable out of this at a time and repeat sufficient number of times. So now calculate the probability of B. So now use the knowledge of, now what we need to do in third case is sample one of the variables. Let us say we are following left to right order and we want to sample B. So we want to sample B. And for that we will generate some random number. So let's say again the random number is 2000. But we want to calculate probability of B. We need to know the probability of B. Right. So in this case, we will use, to calculate probability of B, we will use now for next 5 to 10 minutes you need to pay proper attention here because otherwise it will sound very difficult. So to calculate probability of B, we will use knowledge of conditional dependence and independence to calculate probability of B. And what is that? Remember our talk of Bayesian network when we talked about the conditional dependence and independence. So the graph, the B is independent of what? B is independent of J given A, but B is not independent of E given A. So given that you have observed A, B and E are not independent. So that was the discussion of conditional independence we had. But for now you can remember it like this. Let me introduce one term which is called Markov blanket. let me first tell you what it is. The Markov blanket is blanket is defined by parent, children, and spouse of a node. So Markov blanket of B is given by what? A and E. Of course, B itself, then A and E. If you want to keep B out of it, then A and E. Markov blanket of B is A and E. A is a child node of B, and E is a spouse or neighbor node of B. What is Markov blanket of J? Can anyone answer this? Markov blanket of J? Look at the graph and figure out the parent, child, and neighbor. So J has parent A and spouse or neighbor Mary calls or M. So Markov blanket of J is A and M. And what is Markov blanket of A? And look at node A and figure out the parent and child nodes, everything, right? Burglary and earthquake are parent of A, and John calls and Mary calls are children of A. So Markov blanket of A is all other nodes: burglary, earthquake, John calls, and Mary calls. Is the notion of Markov blanket clear? What is Markov blanket? So Markov blanket is parent, child, and spouse node of a node in the graph. And why this notion was important here is because we want to define something. A node is conditionally independent of all the nodes in the graph given its Markov blanket. So if I want to calculate probability of, what does that mean? If I want to calculate probability of J given everything else, that is B, E, M, and A, then this is equal to probability of J given only A and M, because A and M are the Markov blanket of J. Right. If you look at the graph here, so if I want to calculate probability of John calls J, then it is dependent only on alarm, right? And Mary is neighbor. So you need only this portion of the graph to calculate probability of J, and you can ignore this portion. Right? So to calculate the marginal probability, you only need to look at the Markov blanket of a node, and you can ignore rest of the nodes. So this helps in reducing the number of computations that we need to calculate marginal probability of any node. And this is particularly useful because usually Bayesian network has in many nodes, like hundreds or thousands of people develop Bayesian network with hundreds of nodes. In that case, to compute the marginal probability of a node is again a raised to n exercise. So if you only look at the Markov blanket and use the idea of conditional independence, then your computation would be faster. So keep this in mind, Markov blanket and conditional independence based on Markov blanket. So when I want to calculate probability of J, I only need to calculate J given A and M. And then of course I can use this knowledge of network and simplify this. Similarly, to calculate probability of B, I only need to look at B, A and E. So B given A and E, which will turn out to be probability of B only. So let's do this. Let me again write this here. So we had sampled B, A and J, all three to be false. And now we want to calculate probability of B. The random number that we have used was, did I generate 2000? Okay, random number was 2000. So let's call X is equal to 2000. So probability of B given everything else is equal to probability of B given A and E. Right. And B is not dependent on A and E. Right. So joint distribution of B, A and E, if you want to model, it can be modeled as probability of B only because B is not dependent on A or E. That will be probability of B, which is 0.001. So when you have sampled X is equal to 2000, B still remains false. So with this probability, again draw a stick of length 0 to 10,000 and 0.001 or 100 up to 10 it will remain here. And when you project 2000, 2000 will go somewhere here. And that's why the second sample of B will be false. Now in next iteration, we will update A. We have 5 more minutes, so we can finish one more sample. So let's calculate probability of A given everything. So we want to calculate probability of A given everything. And from our Bayesian network, we can see that probability of A is probability of A given BE. Okay, just a second. So we need to actually model this joint distribution. Probability of A given everything, that is B, E, J, M. Which is simplified to probability of A given all of them, right? It is all of them. Here it is not dependent, so it will be all of them. So it can be probability of A given BE into probability of J given A into probability of M given A. And we want to calculate this for A is equal to true and for A is equal to false. And whichever region is higher, that will be the blanket. So probability of A given BE, and now B and E, we know the value of B, E, and everything else, right? So the values of E and M are fixed to be false, and B is also false, and J is also false. So everything is false. So this will be probability of, let me further simplify this. You need to calculate two parameters, probability of A is equal to true given B is equal to false, or in our notation it is probability of A given not B, not E, into probability of not J into A into probability of not M into A. This is one probability of A to be true, and for A to be false, it is probability of not A given not B, not E into probability of not J into not A into probability of not M into A. So once we get these two values, we again draw the stick. We again draw the stick and we define the region where A is equal to true and A is equal to false. And again we sample next variable. I guess we are running out of time. So we'll finish this computation next time. I will tell you how to simplify this and how to compute this. But remember this in mind, that we use Markov blanket idea to calculate the probability. And while sampling, we sample one variable at a time. So first we sample for F, then we sample for A. So in second example, it is all false. Then in third example, F is fixed and A is sampled and maybe A is equal to true. Then in third example, F is, we will sample J and maybe J turns out to be true, and so on. So after every sample, one variable value is changed. Other value remains same as the previous sample. And it is said that if you continuously do it for sufficient number of times, the Markov network would become stable and you will get the samples which are true to the distribution. But that we'll discuss next time.